Session 7, Kubernetes Cluster Architecture. In Kubernetes, what we have is we have masters and minions, Kube API server, etcd key value store, Kube scheduler, Kube controller manager, Kubelet, kube-proxy, and kubectl command line utility. Let's understand the importance of each one of these in detail. The architecture is the Kube API server is the main server listening on port number 6443. Whether you are using kubectl command line utility, through this you send the request to the API server on port number 6443, or you are using dashboard like user interface, so you send the request to API server. So the API request is sent to the API server on the master. So all requests goes to master where we have API server running. API server also have scheduler and controller manager which helps API server. etcd is the distributed database where we store the Kubernetes cluster state and the configuration data. So this is what we have the master. On the worker node, we have a kubelet agent running and kube-proxy running. The internet connections are handled by the kube-proxy, and Kubelet interact with API server to manage the cluster. The containers are handled by Docker or any other runtime. In our case, like we are using containerd with Podman, where we manage the pods and containers are inside the pods. You can see that this figure, this is single container, this is single container, this is a 3 container pod. So these are pods. So these are managed by Docker or Podman, and the Kubelet is taking care of this through the Docker or Podman to manage these containers. This is worker node. This is the architecture of Kubernetes. And the requests are handled by proxy, which will forward the request to the appropriate pod. So on the master node, we have a API server, scheduler, controller manager, and etcd. So how Kubernetes works? The master controls the cluster and the nodes in it. So this is the master which will control the nodes and everything, where we have the container management system running. The nodes host the containers inside them, and containers are inside separate pods. Like this is the pod, this is the pod, these are all pods. Pods are logical collection of containers which need to interact with each other for an application. Replication controller is master resource to ensure that the requested number of pods are running always on the nodes. Service is an object on the master that provides the load balancing across replicated group of pods, because if you have 2 replicas of the pod running, one here and another here, so where the request will be sent, that will be decided by service. So this kind of load balancing will be done by service, which is running on master. How that will happen, remaining training will focus on this aspect only. So Kubernetes master machine components. First is the API server. Kubernetes is an API server which provides all the operations on the cluster using the API. API server implements an interface, which means different tools and libraries can readily communicate with it. Then we have controller manager on the master. This component is responsible for most of the collectors that regulate the state of the cluster and perform a task. So therefore it can be considered as a daemon which is running in non-terminating loop, and is responsible for collecting and sending information to the API server. Scheduler is one of the key component of Kubernetes master. It is a service in master responsible for distributing the workload, meaning whenever a manifest file, simply manifest is what we call it as now onward. When a manifest is sent to the API server, controller will watch for it. Controller will tell scheduler that, hey, we have a request, we have a manifest, kindly look into it. Scheduler will see that is it a change request, it is an update request, or is it a new request where I have to create a resource. So it will find out where I can put it. So this is responsible for distributing the workload, which is in the form of manifest file only. So it is responsible for tracking utilization of workload on the cluster nodes and then placing the workload on which resources are available and accept the workload from the cluster. So this is the job of scheduler. In other words, you can say that it is a mechanism responsible for allocating pods to available nodes. The scheduler is responsible for workload utilization and allocating pods to new node. That's the job of scheduler. etcd etcd stores configuration information which can be used by each of the nodes in the cluster. It is a high availability key value store that can be distributed among multiple nodes. It is accessible only by Kubernetes API server as it may have some sensitive information. It is a distributed key value store accessible to all. Then we have Podman. The first requirement of each node is Podman and containerd, which helps in running the encapsulated application containers in a relatively isolated but lightweight operating environment. Then we have Kubelet Service. This is a small service in each node, responsible for relaying information to and from control plane service. It interacts with etcd store to read configuration details and write the values. This communicates with the master component to receive commands and work. The kubelet process then assumes responsibility for maintaining the state of the work and node server. That was the master. So what we discussed, all these components were the components on the master. Kubernetes node components. Kube-proxy. Kube-proxy to manage individual host subnetting and make services available to other components. A small proxy service called kube-proxy is run on each node server. This process forwards the request to correct containers. It can also do primitive load balancing and is generally responsible for making sure that networking environment is predictable and accessible but isolated where appropriate. Pods. Containers are themselves contained in the objects called pods. Pods are made up of one or more containers that work together and share the life cycle of on the same node. For example, a pod may consist of a main controller that runs application server and a helper container responsible for retrieving files when it detects the changes to the external repositories. Like this, container, and this is a helper container, this is a main container, and this is taking care of the storage part, that part. So Kubernetes cluster manages each pod as a single unit. So the minimum manageable unit in Kubernetes is a pod. Kubernetes service. This service object, Kubernetes object expressing pod networking endpoint, that is internal or external IP address. This is what is known as service. Service is associated with pod through a label selector. Now let me explain the label selector concept. When we write a query in a relational database using MySQL or Oracle PLSQL or whatever, You write query something like this: select name, age, phone number from employees table, where name equal to this, age greater than this. So this where clause is to filter, because if you don't use where clause, it will fetch all the data which you are not interested. You are interested into selected records only. So you will specify a filter. So the filter is where clause, where you specify the name starting with A and age greater than 27. That is the filter you are saying. This is the same mechanism throughout Kubernetes resources, where these two components play very crucial role. One, you create labels for every resource. Second, the coupling, the association, the relationship of these resources are done by selectors. For example, a deployment has to manage specific number of pods. So what you will do is you will create a label in pod and a label selector in deployment. Similarly, the service part, as I'm explaining here, you will create a label in the pod and label selector in the service, so that you can tell the service object, whatever service object you are creating, that so and so pod matching with this label are to be managed by this service. So keep on creating service object, but then for every service to address or to cater to a specific pod or group of pods, you have to create the label selector. This also helps you in creating and setting up multiple pods to be managed by the same service, to be serviced by the same service object. That's also important point here to understand. So service is to associate the pod through a label selector, is associated with pod. D is missing here, through label selector. Like cluster IP. Cluster IP, it is exposed on cluster internal IP address. Node port, if you have 4 nodes and a master, then on a given port of every node the service will be available. So wherever the request comes on a given port, the request will be forwarded to the service, and the service will take care of sending the request to the appropriate pod wherever it is running. So it may happen that you are sending a request to node 1, but there is no pod on the node 1. So ultimately, it is not, you are not sending the request directly to that. It is a service which will take care of the request to be forwarded to the appropriate pod wherever on whatever node it is running. Load balancer, you want to give the external IP through the network load balancer service offered by many cloud providers. External name is for a DNS name server, like domain name. So the manifest file, which I explained before I started this lecture, it is a YML file to declare desired state of Kubernetes object types. You define the Kubernetes type here by means of this kind keyword. Kind is service. Type specifications, like where you specify the spec. This is type is load balancer. Labels and annotations, this is the name metadata, like name is this. There is no label here. And metadata. So all these things are, and this is the selector I was talking about, the where clause. Where app is, this means where the name of the app is, this is the key value, and this is the key, and this is the value. So this is the selector. When the key is app and the value is this, please address that, and that pod will be managed by this service. What is the name of the service? This is the name of the service. So let me explain the same thing again. This is what I was explaining. This is Sage Math Single service will cater to all the pods which have the label as app with a key app and the value of SAGMath app. If this key and value is available with any pod, this is going to handle that request. Where the request will be forwarded, this is the type and ports and all that. session affinity, client IP, ports 8888, protocol TCP, target port 8888. So we'll discuss that because the dedicated session on the service. Right now our focus is to understand the manifest file, not the service, to be honest. I just as a use case I'm explaining it, because I'll be talking about everything here with all the type of resources we are going to create in Kubernetes. This is one simple example. Kubernetes Dashboard is user interface for interacting with Kubernetes cluster, where you can create, update, or delete objects. It is a visual representation of the state. You have to take care of the property, I mean the security of the dashboard properly. Because of this reason why I have pointed out here, this point here, because the dashboard was available as an add-on OCI when I was delivering in 2018, 19, 20, but it was removed later on because of the security reason. So you have to ensure that security of the dashboard. So more on this is at this link given to you. Scaling the nodes. How can we have multiple nodes? How can we add that nodes to the cluster? There are two ways to do it. One is the way you created. You keep on create another virtual machine and let the machine join the cluster using the join command. That is manual scaling. There's also a way to do auto scaling. Means adding nodes, provisioning nodes, terminating nodes based on the load, CPU or memory. That depends on the service provider. As an example, OCI has this facility, AWS has this facility, these cloud providers have these features. By means of something known as instance pool in OCI. We create an instance pool because when we create a cluster in OCI, we create an instance pool actually consisting of 3 nodes. The instance pool is created and we can always attach a policy to the pool with by configuring that what should happen if the memory usage or CPU uses go above a certain level, above a threshold, or what should happen when it drops below a given threshold. So node should be provisioned or node should be terminated. These policies can be created in instance pool as we talk about in OCI certification training. So automatic scaling is possible. It depends on the provider, and also you have to ensure that you have stateless workload. You have to take care of this to handle the load and availability. Pod scaling is also done manually and automatically. We will discuss both in our training. Like we will discuss auto scaling also with example HPA, and manually scale by increasing the pod replica set count. That also we are going to do. Provide custom metrics for scale operations. That also we will see. Rolling deployment is a very interesting concept in Kubernetes, and because of this I think Kubernetes has become very popular solution. Imagine this: you are handling a cab booking system and your entire cab booking system is running on 4 different pods because you have created replicas. So these 4 pods are created to handle that all the requests. Now you have upgraded your image, you have made some changes in the source code, and you have created a new image for this application. So how will you deploy this so that new application is available with the new image, new source code, new features? So what you can do is you can create a window wherein you can terminate one and insert new pod. So this is called rolling deployment. Of course you need minimum 2 and then more than 2 as many depending on your policy, because multiple factors will come here. Like when we are provisioning one, terminating one, so there will be a surge of 2 here, because if we have a limited that we can have 4 replicas, one is terminating, one is provisioning. So provisioning will add one value. So we'll have surge of 1, sorry, not 2, surge of 1. But if I say that you can create two new replicas at the same time, that is called again surge of 2. So if you terminate 2, add 2, so this maximum unavailable is also important, that how many of them you want, that maximum how many of them can be unavailable. Like out of 4, if you are terminating 2 and the new 2 has not been provisioned, that means you are making 2 unavailable out of 4. Can you afford that? All these settings are configured in rolling deployment, which will focus on the topic called deployment. So where we'll decide, okay, we want 2 to be available always, 2 can go down, so that we can add 2 new and terminate 2 old. So this is how the rolling deployment happens. The deployments are high level objects that developers work with directly to manage the life cycle of pods. They describe the desired state of an application. When deployments get modified, Kubernetes automatically adjusts all replica sets, which make it possible to perform updates without affecting application availability. So we can ensure the zero downtime, also means 100% uptime. The conditions are: deployment must contain more than one replica. Pods are incrementally updated. Configurable update schema like maximum unavailable, maximum available, maximum surge, all these things are possible. And you can also roll back to the previous version. Again, this is not the right time to ask questions on the deployment, because we have full comprehensive session on deployment with appropriate lab assignment. Service. Pods are only accessible within the Kubernetes cluster, so to make your application available to the outside world, pod must be exposed as a service. A Kubernetes service groups together related pods and present them to the end user as a single entity. Role-based access control. This provides granular access to the resources and operations, but you must enable it first on the cluster. You have two types of roles here. One is the role or the cluster role, which represent a set of permissions, or in API terminology, set of verbs. View, edit, delete, these are all verbs. By means of verbs we configure this. Role binding, you bind the role to an identity. To be precise, service account. In Kubernetes, the identity is also referred to as service account. So in order to create a new user, the first step will be you create a service account. Second, you create a role with appropriate verbs. Third, you do a role binding of the service account with the role. So you create application role or cluster role, and then you bind the role with the identity. This is what the role-based access control, how role-based access control can work. We will be doing role-based access control also, don't worry. More on this at this link. That's all for this session. Recording is available. You can watch the recording at the link given to you.